Thank you. So I don't know if my presentation is too technical after what I saw from Daniela and Sinan, but I'm going to try. I'm not going to take more than 10 minutes, okay? So basically the idea, I work on, my lab is called Battery Materials Lab, and I try to work on next generation batteries from a materials perspective. So why do we need batteries? Every day we use batteries so much more. These days we're really into electrification of cars. Obviously we use them every day in our cell phones, but also for making renewable energy a more viable reality, we need to store energy, and that's what we do with batteries. So in a battery, I just want to give some background information for those of you who have never, encountered it. In a battery, what you have are lithium ions, so lithium plus. And then you have the two electrodes, which are different at different voltages with respect to lithium, and they store the lithium inside of themselves. And how much lithium you can stuff, I like try to make it easy, like how much lithium you can put into an electrode basically determines your energy density, how much, watt hours you can put into a certain volume. And the other thing that determines this is power. So actually Sinan was talking about like power as well. So power is how fast you can expand that energy. And so that happens if we look at it from a battery perspective, how fast we can move these lithiums from one electrode to the other. So in order to move the lithium from one electrode to the other, we have to first take it out of the electrode, and then we have to transport it all the way here, and then we have to stuff it into the other electrode. So usually what we do have in normal lithium ion batteries is that we have a liquid electrolyte, this intermediary that shuttles lithium back and forth. The problem with this liquid intermediary is that it is flammable. So we've all seen like battery fires and everything. So it's very safety wise, it's not very good. So what we want to do in reality is that we want to increase our energy density, how much energy we can put into a certain volume. And the way to do that is by basically changing the material that we currently use, which is graphite, which only gives you about like 200 milliamp hours per gram. We would ideally move into pure lithium metal. So that means that we don't have any dead weight, and we would like to have only lithium on one of the electrodes. And then we have to find a suitable cathode on the other side to stuff the lithium into. So pure lithium metal would like almost 1 order of magnitude increase our energy density. But the problem with lithium metal is that it forms these dendrites. So these dendrites are basically these protruding, lithiums or lithium dendrites. What they can do is if these dendrites touch the other electrode, the flammable electrolyte takes flame, like it's flammable, so it creates a fire. So the solution to all of these problems that we have is by basically letting go of the liquid electrolyte. Instead of using liquid electrolytes, what we can do is we can have a solid electrolyte. So this intermediary that shuttles the lithium back and forth, instead of having a liquid, we can have a solid. So not only does solid stop the dendrites, so it just acts like a mechanical barrier that keeps the lithium dendrites from touching the other electrode. Not only does it do that mechanically, it also is, non-flammable. Here you're seeing like an electrolyte that actually goes into a flame, and it doesn't take, and catch fire, basically. So these solid electrolytes are basically what I'm working on, where you move the lithium through a solid. And so obviously moving something through a solid is not as easy as moving it through a liquid, because liquids are very non-viscous, compared to solids. So liquids are easier to move through. However, there are some, lithium conducting solid electrolytes that have conductivities of lithium that are close to the liquid case. So here we are seeing the benchmark, this, organic electrolyte, this, green spot or green line. You can see that all of these other solid electrolytes, they are trying to, they're trying to get close to it. So there are some solid electrolytes that can have the same power density, that can have the same conductivity, meaning like the speed to shuttle lithium back and forth. So we have that. We have solid electrolytes. They don't take, they don't catch fire. They can shuttle lithium back and forth at really high speeds. But then the problem becomes the interfaces. So here in this, battery, you have this interface between lithium electrolyte, this solid, and this cathode, and then you have the interface between the lithium and this other solid electrolyte. So these interfaces are basically what are the most problematic. The interface between lithium and these solid electrolytes are, a lot of work has been done there. And you can see in this one, for example, that this droplet here is the lithium. And then here at the bottom, this surface is a solid electrolyte surface. We were able to compatibilize these two materials and have them contact each other, easily. However, the problem that we are currently facing to have a high power density solid electrolyte, which will be extremely safe, is that the impedance between these two materials, these lithium cobalt oxide, and let's say this solid network, which we take as LLZO. This is one of the most promising solid electrolytes, and this is a very common cathode material. The thing is, this interface is like the thing that's keeping these solid batteries from being highly commercialized. It's because there is a high impedance. Impedance meaning the lithium cannot cross over through the interface. And the problem with this interface is that it basically, when we put these two materials together, they make secondary phases. So they come together and they react, and these reaction products stop the lithium from crossing over. And so what we call interphases, basically. So how do we bond these two oxides together? Is that another problem? Is that in order to bond two solids together, you need to sinter them. Sinter them meaning heat them above 1000 degrees over 10 hours. So that's a really high energy process. Ideally, and we found that basically through my research, through my postdoc research, is that if we combine these two materials together, if we put them next to each other, and if we try to bond them together by sintering, by heating to high temperatures, there is a lot of secondary phases that form here, like lithium carbonate, lanthanum cobaltite, lanthanum zirconate. These phases form, and they really stop the lithium from crossing over. And so ideally, what we want is this new technique that I'm working on right now in the lab, which is called cold sintering. So cold sintering is different from just conventional processing where you heat it up to 1000 degrees. Instead of doing high temperature sintering, we would combine these two materials, this solid electrolyte and this cathode, at around room temperature. The problem or the difference is that we would use a solvent and pressure in order to fuse these materials together. And so this is a technique that was highlighted in 2016 by Clive Randall at Penn State. And we're trying to apply this cold sintering mechanism to solid state batteries. And here you can see that you have, solidified and made very nice interfaces here between, in this case, silver and lithium manganese oxide by cold sintering. And you can see the interface is very sharp and non-degraded. So Basically, cold sintering is a very simple method, and that's what we are doing in our lab here as well. You are taking a material, you are mixing it with a solvent, and then you are heating it and you're pressing it at the same time, which is what you're doing here. And there are a lot of parameters that you can control in order to make these interfaces, better or more compatible with each other. But the idea is that being like solidifying ceramics at these really low temperatures, like 180 degrees, is very advantageous because we know that high temperatures degrade these interfaces. So basically, there's lots of demand for batteries, and we really need to improve safety and energy density. And the best way to do that is by using these solid electrolytes. But we have trouble at this one interface that we really need to solve before we can use these solid batteries to get a lot more high energy density. And so we are trying to look at lower processing temperatures that will reduce impedance at that interface. And that's what I'm currently working on, is like lowering the processing temperatures and still having a working battery. Thank you so much. I hope it was informative. Let me know if you have any questions. I'd be happy to talk more. Thank you so much.